Muito bem. Hoje temos o último seminário do ano. Eu tenho o prazer de apresentar a vocês o professor Alfredo Goldman. Normalmente chamaria de Alfredo, né? Ele é professor associado do Departamento de Ciência da Computação do Instituto de Matemática e Estatística da USP. A área de interesses dele é, mais ou menos o título da palestra já nos diz, Computação Paralela, certo? Ele fez mestrado na própria USP, que eu me lembre, agora estou lembrando, em 1994. Depois terminou doutorado na França, no Institut National Polytechnique de Grenoble, isso? E ele participa de vários comitês, revistas, etc. Não vou falar tudo isso, porque seria muito extenso, roubaria o tempo dele. Os interessados podem olhar na internet o anúncio do seminário. Por favor.
Obrigado, Tomás. Então, é uma honra estar aqui no seminário da Unicamp. E só para corrigir, o Tomás não tem que chamar de Alfredo, tem que chamar de Alfredinho. Que é uma coisa um pouco mais antiga ainda. However, I'll do the seminar in English because I brought my own foreigner here, and yes, and she still does not speak Portuguese. She will understand soon, but anyway. So, the idea is to talk about generics. I'm not talking about anything very deep on parallel computing. I'm just talking about general parallel computing. So the idea is that just to say to you that are not specialists that this area is nice. And my big message will be like this. That means somehow we are still doing this with computers. That means programming it by changing parts. This is the main message, and let me see. Okay. Give you a little bit of introduction. I did this presentation with the help of several of my students. 3 of them are already professors in several universities, and the other one is still doing his PhD. And I know these seminars from the Institute of Computer Science of Unicamp from '92. I started to receive this list in '92, and I was saying to Thomas that in '92 I did my first bad reply all. So I sent a message to the whole list, and it was a message to a friend of mine. It was not nice. So at least at that time when I did it, it was just to few hundred people. Today I think there are thousands of people, much more than that maybe.
Most students.
And the students and all. So a little bit about me. So I'm old. So I have some experiences on France, US, and anyway, let's go. So about this talk. This talk could be a whole semester course because there's a lot of things that I'm doing. I'm just giving a few glances about it, but there's a lot of material. And there's a lot of information. So we are going just to see few highlights, and my idea is to motivate you to see this area, that how can it be interesting. And if you want to ask me any question at any time in French, Portuguese, English, just go ahead. Okay? Don't be shy. Usually students at the University of São Paulo, they are shy. You are not shy, I hope. Of course not. Great. Great. So the first motivation to do parallel computing is about the speed of light. Usually we think that speed of light is quite fast. But if you do a kind of very simple mathematics, we can see that in a very simplified way, in a small slide, I can tell you that the clock of the processors is limited to 10 gigahertz. In a very simplified way. I'm not talking about anything else. I'm just talking about the speed of light. Light has to across a distance, has to come and come back, CPU, memory, and so. Just looking this, we have this problem that the light is not so fast. There are several initiatives to minimize this problem. For instance, cache memory. Everybody knows what is a cache memory? It's a memory closer to the processor where instead of going to the main memory, I can get data from closer. However, even we can have several levels of cache. The closer will be the faster, however, it will be the smallest. So sometimes I cannot put everything on cache. I have to go to other levels of cache or even to the main memory or even to the disk. And this is really slow. Just to have an idea, to go to this place, it's even DRAM, it's more than 100 cycles. This is a lot. Every time that your program has to go to the main memory, it takes a lot. And there's several initiatives to minimize the problem of the light being so slow. This is some of them. And I'm going to talk, this was the motivation to appear the parallel computing. And I'll give you a kind of history of parallel computing. There was a lot of research. Until 90s, 80s, we had a lot of research on algorithms, parallel algorithms. Do you think that there was any parallel computing in the 80s? What do you think about it? Is there any parallel computing? An old one, 80s? Almost all sequential. The idea is on the 80s I have just one processor. The processor could do several tasks at the same time, doing kind of multitask. But it was not parallel computers. What we had at that time was models like PRAM. Have you ever heard about PRAM? Parallel RAM. Parallel random access machine. It's a computer that supposedly has an infinite amount of memory, an infinite number of processors, where I can communicate with everyone, every processor in just one cycle. Does it appear reasonable? This was the model that we had at that time, and several models from that. So this was the research that used to be done until the 80s. On the 90s, we started to have some computers, some parallel computers. And then these parallel computers, we had to interconnect several computers, several processors. And the way to do it was the main research, to find how to interconnect processors in a nice way. From that time, we have the very famous hypercube. I think you have you ever heard about hypercube? It's a nice topology and everything. And the research was much more on network cards, to make the communication fast, to have computers that was with the right communication, with the right network card and things like that. On 2000, we have the Beowulf appeared. What was Beowulf? It was a project that you can build your parallel computer yourself. How can you do it? Going to a store, buying commodity hardware, and putting this commodity hardware together with a network card. This was the most on 2000. And this was the appearance of the first clusters. And a little bit after, we got the grid computing. Where is the grid computing? I have the clusters, but I can share my clusters with other users, other people. So this was kind of the research line going historically. More recently, we start to reach the limits of the clock. What does it mean? Until 2000 something, it was easy to have a faster processor, increasing the clock, having more area, and just making it faster. having more logical units, make it faster. And we were reaching the limit. So it was not so easy to have a so strong processor, and we start to have multi-cores. What is a multi-core? Instead of having just one single core, I have several cores on a processor. Okay? And also, we start to do virtualization. To allow virtualization, it was a very important thing that the hardware primitives start to allow that we had to have virtualization. What does it mean? I can have computers inside a computer. I can put virtual machines running on top of a processor, and I can have several virtual machines working. And then we have the idea of cloud, that is a place where I have computer capability and I can run programs over there. And also the fog. What is the fog? Maybe sometimes to go to the cloud is too far away, because maybe the cloud is in another country even. Why to go to the fog, to the cloud, if I can go to a near cloud that will be the fog, the edge? Oh, sorry. And okay.
Fui eu.
Oh.
Okay. Oh.
And then, more recently, we start to have a very large use of SEMD computations, single instruction, multiple data. And this is what you have a lot in GPUs. In GPUs, we have this. We have a lot of very naive processors that do very simple computation, but a lot of them. And accelerators also. And just to talk a little bit about the future, we're going to have FPGAs, that's field programmable gate arrays, a way to make something not closer to the hardware, but programmable by software. And the memory is changing. Here at the UNICAMP, we have several professors that are doing research on persistent memory, non-volatile memory, and we can also put some memory to do computation. We can ask the memory, do some computation. And this is another way to do it. Any question by now? Are you still alive? Not sleeping yet? So, I'll talk a little bit about the evolution. And for it, I took a picture of the summit. Do you know what is summit? What is summit? Top one computer of the world. Top one, that means the faster. And how can I measure if a computer is faster? How can I say that this was the top one?
Operation per second.
Not operation per second, because there is operation per second, it's a very naive thing. Because even if I have a operation per second at top possible speed, this is not really feasible sometimes. For instance, if I get 1,000 computers, but them without communicating, I have 1,000 times the computer. This is not feasible. I have to do communication. So, to be able to know what was the faster computer in the world, it's very important to have a benchmark. Kind of parallel programming that try to understand how fast is the computer. So there was this top 500 list that was created, and it's based on LINPACK. It's a linear algebra library to do computation. So I have a way to compare different computers. Okay? Let's talk a little bit about this top 500. Let's take the old times, from 1990 to 2001. We see the decline of computers with one processor. At a given time, 20% of the fastest computers of the world just had one processor. 93. We also see the decline of machines that are single instruction multiple data. The same that we have in GPUs now, they have this golden era here, and then they start to disappear. You see? The same technology, the same idea, single instruction, multiple data. And we see that machines with shared memory, they start to be very well known, and then they disappear. Oh, sorry, SCMD is here. I'm a little bit colorblind, so I mix the colors. I don't like colors that much. And shared memory here, they start to get and then they decline. We have this kind of dedicated machines that start to get over. What is dedicated machines? Machines done by big companies. And we can see that something appearing here, the clusters. What's the difference between a cluster and a dedicated machine? There is someone that makes a dedicated machine, a big company that does it and sell it as is. In a cluster, you can buy the parts and build it for yourself. And then from 2002 to 2010, we can see the confirmation of the clusters. The clusters came to stay, and this is until today. There's no big difference. There's still some space for dedicated machines. Machines that are built exactly for you to do something specific thing, they are still here. Why these machines are special? Mainly the interconnection network, it's more powerful. Okay? The other types just disappear, you see? They are just clusters and dedicated machines. And a curiosity, we have the appearance of computational clouds. For instance, in 2010, I think this was the cloud from Amazon. They did a test on Limpack, a real test on the cloud, and it was the 233 fastest computer in the world. And there are several years where I could get the information. It was 42nd fastest computer in the world, a cloud. What does it mean? We have a performance benchmark. If we run Limpack, we are going to see what's happening. So it is possible to do that. And for instance, what do you think? Do you think that do you think the cloud is faster or not than a computer on top 500? I got one no. Just one no. I got two no's. Two no's, several unknowns. So let's do it like Rodolfo do with me. Rodolfo, what do you think?
It can be faster, but usually you're not going to pay for that.
It can be faster, but you usually are not going to pay for it. Why? Does anyone here use clouds? Does anyone here does not use cloud? Everyone uses cloud. Clouds do not need any more marketing. Could you imagine the price of stopping a cloud just to run a benchmark? Amazon say, oh, I will stop the cloud tomorrow. You're not going to use it. Stop all the services, and I'm going to be on top 1 of top 500. Does it make sense for you? Why? They're going to lose money. This is the main business. So sometimes, if the cloud is idle, they can do this kind of tests. Otherwise, there's no reason. They do not need to sell the cloud. Everybody's buying it already. Okay? So, I would say that maybe the clouds from Google and Amazon and big clouds are among the top 10 computers. But no way to know it for real. Another change, it's about accelerators. They came to stay. And we can see that Xeon 5 was a kind of bet from Intel to have an accelerator with kind of very powerful processors. It was good, but then it's going down. And we can see that different families of GPUs are going well. What I want to say about it? What you can see here's I got the day, the year where this architecture started. For Tesla started in 2006, and it was 90 nanometers. Fermi 2010, 40 nanometers. Kepler and so on, until Turing 2018, 12 nanometers. What can you see from these numbers about GPUs from NVIDIA? What can you see? What do you see?
The size is becoming smaller.
The technology is becoming smaller, but a little bit smaller, up to 7 and something times, but it's quite stable. But there are more information here. Do you see? From here to here, 4 years to have the new architecture. And then 2 years, and then 2 years, and then 1 year, 2 years, 1 year, 1 year. What does it mean? These GPUs are evolving very fast, are becoming very powerful. Okay? This the main message. And has anyone here have a computer without a GPU? Without. You have a computer without a GPU?
I mean, it's not dedicated GPU, it has an onboard GPU.
Has a GPU.
Yeah, sort of.
Even your cell phone does have a GPU?
Probably. I don't know.
So, GPUs are come to stay. We're going to have GPUs because they are very efficient for a special use. I like this image where you can see the dominance of operational systems. I particularly like to see that there is, when you talk seriously, there's no place for Windows. Okay? And this is a good question. I'll try to see if the students from UCamp are better from that, or ours from USB. For servers, the market is based on Linux. For high-performance computing, also. Why does people still have Windows on their desktops?
Everybody else does.
Well, for gaming.
Gaming is a good question. Good answer. Very good answer. What else?
Well, applications like Photoshop and video manipulation applications that aren't compatible with Linux, an example. Like an example, I still have Windows on my laptop because I use Photoshop a lot. There isn't Photoshop for
GIMP
Linux.
is nice.
What?
GIMP.
Oh, I don't like GIMP. It's nicer.
Anyway, but the idea is that if you want to do computer science for serious, you do it with Linux or something based on Linux. And here it's also so just I'm just trying to provoke you to react a little bit more. And just him is reacting. Okay. But keep reacting, okay? Keep saying. And this was a very important thing that was happening. You can see that until 2015, the distribution about countries on the top 500 was a little bit stable. However, we can see that there is a big player that starts to appear and it's getting more and more share of the market. That's China. And is it the end of the domain on technology from the United States? And then this was what's happening in 2017. And then there was even 3 reasons why Trump is backing exascale computing. To say, okay, we need to be the first ones to have exascale. So, is it interesting for one of country to have a top computer?
What's the fastest in Brazil?
Oh, Brazil is Santos Dumont.
What's the position?
Oh, it will be about 250, 300. I think when it was bought. Now it's Brazil. We usually have the fastest computer just for one edition. The top 500 goes out 2 times a year. Usually Brazil it's over there and then no more, and we have to buy a computer and it's not stay alone. But what's the importance of having a faster top 500 computer in your country? Why can it be used?
Research.
Research, yeah. Research, yeah. I like research. But it's not the main goal. For instance, do you know that almost all developed countries are against tests with nuclear weapons? Why?
Which countries?
They are against doing tests with nuclear weapons.
Developed countries, that's what
Developed countries. They used to do it. They do not do anymore.
simulate.
They used to do it. America used to do it, these tests on deserts in the middle of the country. France used it to do tests on Krakatoa Atoll. And now they say, this is not good. It's wrong for the environment. Stop doing it. Why they do it? Why they say it?
Because they already have nuclear weapons.
They have nuclear weapons, this is one point. But they can have better nuclear weapons. How can they have better nuclear weapons without doing tests?
By simulating those tests in
By simulating.
in a high performance supercomputer.
Why they did the tests before? To learn, to be able to model, to be able to program, to be able to have the computers with all the software able to simulate these weapons. So, these countries that say, oh, we don't have any more tests on nuclear weapons, they're not being good saying, okay, we are good now, we do not need anymore, it's bad for the environment. They have just good simulators now. They do not need to do any more tests. So, a top 500 computer can do a lot of simulation. Okay? So this is one reason to have a computer like this. I'm not saying that it's good to have nuclear weapons, not at all. I'm saying that it is one of the reasons to do simulation. And more than that, to have simulation on climate, weather, and several other things. But after 2017, the situation changed. The 2 fastest computers in the world are from America. Summit and Sierra. Both are strongly based on NVIDIA GPUs and processors from IBM. The third one, that it's the Sunway, is based on a self-made processor. China made a processor from scratch, a new processor. And the Sunway was the fastest computer in the world some time ago. And are we far away from exascale? Do you know what is exascale? If you take a look at here, peak performance, 200,000 teraflops per second. Okay? If you multiply it by 5, we are in exascale. Okay? And so, are you far away from exascale or not? What do you think? The answer is just below. Depending on the precision, we are already in exascale. If you take Summit and do operations in half precision, we are already in exascale. Rodolfo, what do you want to say about it?
You just
Okay, you can say no, whatever. So, here I got some numbers from Summit. Double precision. Why double precision? When I want to do real simulations with real data, I need almost always to have a good precision. Otherwise, my data is not so meaningful. So it has 200 petaflops. Sierra has 125 petaflops. And this is the size of them. So, half precision, node performance 700 teraflops. And if you multiply it by the number of the nodes, you go beyond exascale. And what is interesting about it? Computing nodes. 9,000 IBM Power 9s CPUs and 27,000 NVIDIA Volta. This is a lot of CPUs.
3 to 1.
Sorry?
3 to 1.
3 to 1. There's nodes with 6 GPUs. And just for instance, you gamers, you would be happy with half a volta. Half a volta would be more than happy. Okay? And the interconnection is very important also. Okay? 4 to 6 NVIDIA voltas for GPUs and a lot of DDRs. Talking a bit about Sunway. Sunway, Taiyu, any Chinese here? No Chinese, okay. Taiyu Light, I can say. I hope there's no Chinese live, otherwise. They did it different. They started in 98 doing other computer that was based on a commercial chip. It was on 5th position of top 500. The Blue Light has already his processor 14th position, and then they got the Taiyu Light. That's currently the 3rd fastest processor in the world. And they did a different processor. They did a kind of trade-off between SCIMD, that has the GPUs, and CISC, because it's not so complex. At the same time, it has a lot of. They have 260 cores by processor, and more than 10 million cores. However, as they proposed this new architecture, there was no application ready for it. So they had to write applications from scratch to get applications optimized to this computer. Okay? This was a lot of work. So, are you convinced that you have a lot of hardware doing parallel computing? Did I convince you there is a lot of hardware? And so, this is reality. We saw, even, for instance, your cell phone, how many cores does it have? 4 cores in your cell phone. So this is a reality. From the cell phone to the top 500, there is a lot of cores. From 4 to millions. And what do we do regarding software to it? What do we have about software? So participate a little bit. I'm going to talk later, but I want to see you all wake up. What do we have about software? Fortran.
Since the 70s.
Fortran since the 70s. And Fortran is still used.
60s.
The
60.
Sorry.
I gave a very similar talk at IAG, and people are saying, oh, why don't you like Fortran?
Why do you like?
They know how they like it because they have a lot of legacy code in Fortran. They have the code, it's working, they need it. Okay. But why keep writing code in Fortran? This is the problem. And I discovered that the problem over there, it was different, a different mindset. Because I was saying, oh, you should not program in Fortran, because programming in Fortran is like using old-fashioned things. And they asked me, oh, what is a kind of old-fashioned things? Oh, I said, oh, using global variables, using goto, and they said, oh, is it bad? I said, oh. Does anyone here in this room use goto? Global variables. Why global variables are bad?
Because they are.
Not bad, bad answer. Why global variables are bad?
Because of the scope of variables. Technically, you could, by accident, create a variable with the same name inside a function or inside a for loop.
Scope. When I have something where the scope is the whole program, I do not know who is dealing with this variable. I don't know who is changing this variable or whatever. So this is why global variables are bad. This is why you do not use it. However, this is not so usual. Maybe in computer science undergrads we know that, but outside, no. So let's talk about it a little bit. This is the problem. Do you see this computer here? Who recognizes this computer? Maybe Flavio will recognize this computer. Okay, just a hint. This is a 10 megabytes hard drive. 10 megabytes hard drive. Like this. And this is the problem. The language that we use are mainly based on things from that time. So, there are people that use Fortran and global variables. Yes. We are trying to parallelize a code from astrophysics, and our main problem was to eliminate global variables. And the guy said, oh, we're going to parallelize? Why are you thinking about global variables? I said, we cannot parallelize anything with global variables. We do not know what's happening. So it's complicated. Do you program in C and C++? Do you use pthreads? Pthreads are from when POSIX threads were defined. When? At the time of that computer. We are still doing it. And then someone will say, oh, this guy. I'm younger, I use Python. Do you like Python? I want that one. Who likes Python here? You like Python, okay. Do you know where is Geo?
I use for data science purpose.
Data science. Maybe data science not so parallel. Why do I need to do data science in parallel? Maybe no need. It's just terabytes of data. I can do sequentially. Maybe. Let's see. Python. First of all, Python is not new. Python has more than 20 years. It's very nice. I like it for teaching first years. It's amazing. However, there's this global interpreted block. What is this? To avoid any possible semantic error, Python does everything sequentially. Have you ever tried to create threads in Python to see if it goes faster? If you're going to do that using data science, you're going to need it sometimes. You have a computer. How many cores does it have in your computer? 16. So, do you want to see it 16 times faster? What's the idea? Instead of using just one thread, I use 16 threads. Okay? Is it going to go 16 times faster in Python? No. the threads are executed sequentially. The threads are executed sequentially. There was a big discussion at the time of Python 3 if they are going to avoid it, but it's very good because it makes Python be correct. Okay, if you want to do it another way, you can use processes in Python. But processes are much heavier than threads. So this is a problem. Okay, let's go. Java. Who likes Java here? No one more. No. Java is nice. I like it. The contracts. We know what's happening. We know the interface. It's so amazing. We know what's happening, okay? However, it's not an option when we talk about performance. So, is there any hope in the future that you can have a language that you can use? Yes. Go, Rust, Julia, and some functional languages. Do you know this language? Who knows any of these languages? Go, Rust, and Julia. Any of them. Any. 1, 2, 3, 4. Okay. We are in a top university. We are talking about the best computer science in Brazil, and you do not know. Is it scary? I think so. Why? Our environment is completely multi-core, even on cell phones, and much more on data science. So this is the main message that I want to let clear here, is that we are still programming with these computers. Why? Because to program, we need a language. To do this language, we use something very old. That is this old-fashioned language. We have to change this mindset. A little bit more about it. So, some problems that we got from the past. Have you ever heard an algorithm is a sequence of steps? This is the definition. Why does an algorithm has to be a sequence of steps? Why do I need to impose this limitation? Maybe some of the steps can be done in parallel. Why don't we try to teach students from the beginning that an algorithm, there are some steps, some of them can be done in parallel. If you do it, the student that starts learning will maybe think about other possibilities. Same thing. Why do we still teach for as a sequential? Why don't you teach for all and say, oh, some particular cases you need to do the for step by step. The first, the second, the third. But this is a special case, not the general case. You see the other way around I'm saying? And more than that, who did a course on concurrent programming here? Raise the hand. Concurrent programming. Concurrent programming? Just you?
Yeah.
Parallel programming. Okay, some more. Because we still use, for instance, have you ever programmed with semaphores, P and V? Is it easy to program with P and V? Why? Why? Because it's really, really easy to end up with a race condition. Something that you did not expect. Okay? So, mutual exclusion, everything. There is better abstractions. Monitors. Have you ever used monitors? The guy like Java. Java, you have synchronized class. It's nice. Is it a good abstraction, monitors?
I don't remember.
No, because they are still too low level. We need better abstractions. So, I cannot let everybody sit here. I have to. Okay, there are some solutions. What are the solutions to adapt the software to this parallel era where we have all this multi-core? First of all, it's get legacy code and put in some magic box that will produce parallel code. It exists? Yeah, it exists. It works sometimes? Yeah, it works. But could you imagine that if a program can take a program and parallelize it in a good way? It's not so easy. So, this one possibility, and it's easy to use. You just put into the magic box and the code goes out parallel. We can use pragmas, like in OpenMP and OpenCC. That means I have a sequential code, and I'll put some annotations on the code to let the compiler knows where I can do it in parallel. This helps a lot in this work, but it's not so easy. When I was teaching my students to do an OpenMP program, it was really funny. I was doing it with my students, and I have me and 2 TAs teaching a class. We are parallelizing a code, and we did a mistake 3 times in a row. 3 different mistakes, and I said, okay, let's end the class. Next class, I will and then on the next class, I presented the correct code. And why is this? Is that because I'm so bad doing OpenMP? Maybe, but no. And then I gave a task to the students. I said, no, I'm not so bad. So I want you to find errors in the tutorials all over internet on OpenMP. They are supposed to find errors on the tutorials. There are 7 different groups. They found 7 different errors in tutorials freely available. After it, what we did? Papers. We published a paper. We have concrete evidence that OpenMP was not so easy. Because when you want to do something very easy, it works. But something more complicated is not so easy. And other thing, we tried to check the performance of OpenMP. It was still the 3.0 for running in many cores. I don't have only core. I want 64 cores. How does OpenMP behaves? It behaves bad. If I do not do any fine-grained thing, it behaves bad. So it was a problem of fine-grained synchronization. This was a thing. So it's not so trivial. There are still some problems. And the other option is to use libraries that have optimized kernels. This is a good option also. If I want to do something specific for data science, I can find a library that runs very well on a GPU. Just an example of OpenMP. The idea, I have my code in C, pure C, and if I want to have it in parallel, I add some programs. Basically, the program is OpenMP parallel, and then I have to explain how to do the parallelism. This is the hardest part. Even here, OpenMP for schedule. I'm saying how to schedule this according to the form. Okay? So, it's quite easy. You start from a C program, you put programs, and you may have a concurrent program that will use all the cores of your machine. It appears difficult for you? For who never saw OpenMP, it appears easy? I just got one more or less. Okay, you. What do you think about it? I don't know. Okay. They are shy, the students. Rodolfo, do you want to say something?
You are using several default values over here. So you can remove some of them, right?
Okay, I can remove defaults.
Well, we can remove like the private I is also private by default, the shared is also shared by default.
But it's explicit, that's let know.
You just want to scare them. You remove some of this. Like non-threads about non-threads, you also don't need them. You could remove for default actions.
I will raise it here.
Okay.
And there's another way. For instance, if I want to generate a kernel, I can also have a pragma on OpenSC to generate kernels. that will be executed on GPUs. Okay? Again, what the message that I want to pass is that I can hide a lot of complexity on saying, okay, I need to copy this data to this other price, and this is what's coming back from the GPU. Okay? This is not, I don't intend to teach you OpenMP or OpenACC. I just want to motivate that we can have a simple program and make it parallel, just adding some programs. And again, the example how to generate, and in OpenMP I can also generate code to GPUs. If you want, we can even generate codes to FPGAs, and then you have to talk to Guido. He understands about it. I don't understand. And there's other options, OpenCL, that is write it once and execute it wherever you want. It's the similar model as Java, and maybe there's some problems. And there's an example, let's skip it. However, what I want, my message about it, it's that there is another abstraction that it's much more powerful than using shared memory, monitors, semaphores, whatever, is communication channels. And the basic idea is do not communicate by sharing memory, instead share memory by communicating. This way we avoid several problems intrinsic to parallel programming, parallel concurrent programming. And this is when I say about Julia, Go, and Rust, this is inside all these languages. Okay? Just to let you know, one option to do parallel programming is MPI. And it's really, really old also. My first program with MPI was in '92, I think. And did not change it a lot. And I can use it in conjunction with OpenMP and CUDA. So, talking about a little bit about big data. Big data. Have you ever heard about big data? It's a kind of buzzword. Everybody uses big data. And there's a lot of tools based on MapReduce. Do you know what was the first tool? It's not written over there. What was the first tool to use big data? Hadoop. Very well known. And then now the tools that people are using a lot now is Spark. That is based on Hadoop and more optimized. Storm for streams. But do you know that the performance of these tools is bad? For instance, there was a tool named HPAT from Intel that was used just to show that you can do better. And it was 25 times faster than Spark. And okay, I'm a scientist. I was skeptical about it. So I got one of my students, master science students, he did the comparison from scratch. We got results that was 12 times faster. And so imagine, instead of using these tools, if you use real parallel computing techniques to have a code to be executed fast. It would be great. But instead, people are still using Spark, Hadoop. Don't you want performance? Maybe you do not want. No. Again, if it's important, you have to do it better. And I don't know, there's not so much to worry about it.
What's the actual behind HPAD?
HPAT, it's similar to MapReduce. They are based on MapReduce also. However, they do communication in a little bit smarter way and do not have fault tolerance. And the advantage of HPAT is that as using it, instead of taking 1 hour, you can do something run the same problem in some minutes. And if it's running in some minutes, you don't need fault tolerance anymore. If it fails, you run again. So it's tricky. Okay. So let's see if the evolution continues. Is there anything changing in the world, or we are going to have the same thing from now on? We have here 120 years of Moore's law. What we can have here, we have kind of this almost linear growth. Okay? And it's keeping, thanks to the multi-core processors at the end. However, we have something new here.
It's not linear, it's your scale is exponential.
Yeah.
Yeah, so it's exponential 18 months. Sorry. It's almost linear in an exponential scale. This is what I meant. But I'm talking in English, and yeah. Okay. Oh. Okay. But here we have something different coming here. The growth that we could see here a little bit in performance. Do you know here it's not? Do you see that it's getting a little bit? It's not here was linear, and here is not. It's going a little bit faster. We can see here the performance of GPUs are increasing more than the usual Moore's law. GPUs are getting faster than it. So, is this good? Is this bad? What do you think?
Can be bad.
Can be bad, because if you have more flops available, if someone asks you, I said, okay, I bought a new GPU, make it run much faster. So it can be bad for programmers. But we have much more power, and the power is increasing in a more faster than before. Okay? And just to let know, this Titan V, the last GPU from NVIDIA, the board itself has 110 teraflops. Just one board. The clock is not so impressive. And the number of processors, is it impressive? 5,000, more than 5,000 processors. It's a lot. And we got the perfect application for it. Deep learning. And everybody is doing deep learning and neural networks. And as to the neural networks, we have to multiply matrices. GPUs are just perfect for it. So this is why this got NVIDIA is getting to get bigger, and this is why we have this Summit and Sierra with too many GPUs, because they have one application, deep learning. Have you ever heard about deep learning? Marcelo was here last week. He talked about the possibilities of machine learning, maybe. So. But we have also something changing memory. We have this persistent memory, non-volatile memory. It changes a little bit. We have the universal memory. It's another technology. We have the ideas. I'm not going to take memory to do computation and take it back. Why don't I take computation to the memory? This is another paradigm. And this, for instance, dot product engine, where I can do computation in the memory. So this is a change that maybe are going to happen soon. And will allow even more parallelism. Processors, arrays, this is really not, I think it's, with the GPUs, there are no more processor arrays. I think it's finished. What do you think, Rodolfo, Guido? Are we going to have it, or? Maybe the Chinese may come out with something different, but otherwise I do not see it. This is a kind of, I don't believe it anymore on it. FPGAs. This is the new technology that I think that is going to change the world. It's the field programmable gate arrays. You can choose what it's going to do after its fabrication. You can program a circuit on the fly. And it's configurable, adaptable, it's efficient on energy, and usually an FPGA now comes with another processor, an ARM processor, to help the FPGA to do things. And what is interesting is that it's possible to go from C to the circuit. This is something named high-level synthesis, where I can write a code in C, and this can generate a circuit on an FPGA. It takes time, hours, but it's possible to someone to program an FPGA without bothering about the logic gates. This can be useful in the future. So, I was talking about challenges. What are the challenges? Memory wall. What is the memory wall? The CPU performance is growing. The memory performance is not growing at the same pace. But to have data, I need to get from the memory or do something. So this is a problem that we have to. This gap is getting bigger, and this is not good. And it just got worse with multi-core. So memory wall is a challenge to have more performance.
This memory wall exists since the beginning.
Since the beginning, but it's getting more serious. It's getting more serious. Each time more serious. This is the problem. Power wall. Even with the reduction of the size of the transistors, the power is still the same. So we can reduce the clock, but reducing the clock, I'm going to reduce the performance or the voltage. So this is another challenge, how to keep doing parallel computing with it. So, is it the end? No. We have this kind of quantum computers. Is this for real? Does it exist? Is it Google putting money in a drain, or is it for real? D-Wave exists? Have you ever bought a D-Wave computer here? I don't know. How many qubits can we have? 5? 24? 50? Did you see it?
If you see, you don't know the speed, right?
Yeah, and more than that, it's very easy to have a quantum computer. Just make a very good refrigerator with 0 Kelvin, and then kind of. So I don't know. Maybe is it for real or not? This will be maybe a big change. And other thing, more hardware, more complexity, more heterogeneity, more potential for problems. And fault tolerance is essential. You cannot live without fault tolerance anymore. Problems like bit flip. Have you ever heard about bit flip? What is bit flip? Okay, so I will scare your students, sorry. In the universe, there's a lot of bad particles that just goes across us, across the world, across Earth, and everything. And they interact very little with us, these cosmic particles. However, as the computers are very dense and have the transistors at very small, tiny area, sometimes one of these particles hit a piece of hardware. And sometimes what it happens, a small bit that was with 0 becomes 1. Or vice versa. Is it bad that for a computer?
Yes.
It can be bad, it can be really, really bad. Just to let you know, it can be bad if it makes your program crash, but it can be really, really bad if it makes your program do the right results. Find different results from what. And you cannot say, oh, it's okay. Okay, so I have my simulation and the result is that. I run it, I know my model, but the result may be wrong. Or a bit flip. And what's the solution? It's to put more software to help solve all these problems. We have to do it with software. Just letting hardware is not enough. And energy. Energy, it's a really big problem. 3% of the whole energy in the world is spent on data centers. 3%. This is a lot. So, this is about what I had to talk. And if you have any questions, I'll be happy to answer.
Perguntas? Legal.
Even before you started showing about quantum computing, I was reminded to ask you about this. What are your feelings about quantum computing? Do you think we can replace the conventional computers with the capacity and the promises they are making for the quantum computing in terms of, because in terms of processing, they also mentioned some challenge about superposition, as you mentioned, about the qubits, and also entanglements, those problems that you have in quantum computing. What are your feelings towards that? And also about machine learning, deep learning. Have you ever tried to make parallel or complex neural nets and the challenge that we have nowadays with big data for making parallel?
Okay, so first question about quantum computing. I still do not believe it so much. The theory is there. All the fundamentals are there. However, the largest problem about quantum computing is the interface. How to put and get data from a quantum computer. And more than that, how to keep it running with a temperature near zero absolute. So I think we are still quite far away from the possibilities of having it for real. So let's do it the standard way. Let's just have the heterogeneity and new devices by now. I won't bet on quantum computing now. Maybe 10, 15 years, I don't know. About machine learning, deep learning, and everything. These problems are really embarrassing parallel. So, if you get a larger computer, you can have more layers, can increase the width of your network. So, it's perfect. So, yes, this might be a problem because it appears to be the solution for all the problems. Everybody now wants to do machine learning, deep learning. And the big problem about it is the lack of the man in the loop, or the woman in the loop. That means just feed data and get the output. This works sometimes, but sometimes does not work. You have some kind of, you need some person in the loop to understand and do it and improve this process. But yeah, this came to stay, and which we have to live with it. I don't like much machine learning, sorry.
Mais perguntas?
More questions?
Do you really think that FPGAs will solve like problems in scale?
because to me it seems that they are like very expensive, at least nowadays, and you can solve the same problems with a generic processor and doing better in terms of saving energy and other things.
I don't think much about it, but Intel bought Altera. Intel today has all the GPUs inside the processor. You have GPUs inside the processor. I think that the future is to have some FPGAs inside the processor and to have pre-programmed libraries that you burn on the FPGA to execute at some points of the program. Why? FPGAs are very efficient for a specific class of programs. When you do it, it will be faster than doing it. But you have to have these pre-programmed optimized libraries just to burn on the FPGA at the right moment and use it.
So switching the context and do the operations and switch back to
For several very specific things.
That makes sense.
Yeah, just complementing what Fred just said. When you do a Bing search today, you are using FPGAs to accelerate Bing. All clusters, Microsoft clusters in the world have an FPGA there. It's not just going to be a long-term reality. It's here. So the scheduling for the transactions is accelerated using FPGAs. And also, when you use Azure and some microservices for machine learning, you are using lots of accelerated engines on FPGAs already.
But you change these FPGAs?
No, it's like Alfredo said, it's dedicated.
It will be easier to just print a new
processor
with the FPGA.
If you print, you have the fixed hardware.
Yeah.
You have, but the library of possibility is larger.
Yeah, that's right.
This is why you print it, and to burn an FPGA, to put a program on it, it's quite fast. So this is the idea. So, but again, this is for the future. By now, there's very specific applications that use it. If you have a circuit that you know you are going to need it, do it in hardware. If you have a specialized machine where you need a circuit, do it in hardware. But when you need several different circuits in different moments of time, then you need FPGA. Hardware is it's much faster than FPGAs.
Mas, bom, então eu queria agradecer ao professor Alfredo pela palestra, que foi muito interessante, especialmente para leigos. Muito obrigado. Né?
Obrigado.
Bom, vai no banheiro.
Pessoal, a lista, senão todo mundo vai a pau.